Hello friends, let's take a look at a very nice interesting problem involving with complex number integration. Okay, the reason I prepared this video is that it was one of the questions from students. The student asked me, how do we integrate 1 over x to the power 5 minus 1 dx? And for me it was a very nice problem because you can actually extend this idea for the general case of n. And in fact, you're not looking for the particular solution. The question rather asked whether it's doable within the knowledge of the IB integral technique. It didn't involve any of the fancy integral techniques such as like a Feynman technique. But let's have a look at how we can actually prove it using the general understanding of the integral calculus as well as complex. Okay, so without further ado, let's get started. So yes, the student asked me about the general case, the particular case of x to the power 5 minus 1 in the denominator, but we can actually generalize for any case of n, when the n is a positive integer. Whether it's possible to integrate within the knowledge that we have in the IB syllabus. And as you can see, yes, when n is equal to 1, it's very trivial because you get a rational function. And then the antiderivative of rational function is simply just the logarithms. Easy peasy, lemon squeezy. Okay, then let's take a look at the case of n equal to 2. Then it gets more interesting. Because if you got the x squared minus 1, what we are urged to do is really to try to factorize, isn't it? So x squared minus 1 will become x plus 1, x minus 1. Okay, so that's great. And if I can do that, like constant over x plus 1, x minus 1, then it gets extra simple because I can do the partial fraction, right? The linear term will have the remainder term of a constant. So if I do the decompose of a fraction, the 1 over ab is the same as, what is it, 1 over b minus a, 1 over a minus 1 over b, things like that, right? So if I see this, then you can see that, oh wow, well, this is actually just going to be the difference of the linear factor on the bottom, so it's going to come out as just logarithms. Don't forget to add constant c. But my point here is, if you can sort of factorize into the linear form, it gets quite trivial. Okay? Well, instead of talking about n equal to 3, let's try to jump onto the n equal to 4, because it's got a lot of factors, isn't it? Because if I see the n equal to 4 case, I got the x to the power 4, and then I can do the factorization using the difference of the square. So I would firstly do the x squared minus 1 and x plus squared plus 1, like that, right? And furthermore, this x squared minus 1 can be put into the difference of a square like that. Then I got form like this. And quite differently from the x squared minus 1, it's not just purely on the product of linear factors. It's rather now the product of linears and the quadratics, right? For which I'm not so shocked, I'm not so fearful to integrate this, because if you actually do the partial fraction of this being in the denominator, at the end of the day, it's really just integral of the linear and then the quadratics on the bottom. And you can already tell, my friend, for the first 3 terms, it will be simply logarithms, isn't it? Well, obviously constant over linear, it's just logarithms. I'm sure it's going to be 8 times logarithms of x minus 1. But if you look at the third one, for example, if I had let's say, 5x over x squared plus 1. I'm not saying the C is such case, but if it was, then it would be simply just logarithms, because I can now arbitrarily make this as a 2x on the top, and then x squared plus 1. And then for the coefficient of a 5, I got to multiply by 5 over 2. And that would come out just as logarithms, isn't it? So now this is going to be simply 5 over 2 ln absolute value of x squared plus 1, like that. Right? So that would just come out as logarithms. The first 3 terms will be just logarithmic. But for the last one will be given as inverse tangent, right? Because as we already have learned, the 1 over x squared plus a squared will be given by the 1 over a arctangent x over a, right? So that is the integral that we're looking at, right? So if I am able to factorize into the linear or quadratics, I'm very confident being able to integrate. So my theory now is that whenever we have x to the power n minus 1, I want to say that I can factorize it by just the linear and quadratics, which will then enable me to integrate no matter what, right? So that's the premise in this case, okay? But you know what? So I think you can try that using the complex number directly, but let me give you a visual demonstration of what we are doing. Okay, let me use the visual proof of the x to the power of n minus 1 can be actually factorized by linears and quadratics, okay, starting with the n equal to 2. So what I'm going to do is to use a unit circle. I got the center 0 circle here, and I'm going to use the radius of 1. And in this time, for the n equal to 2, what I'm going to do, all right, is to separate the circle by 2. Okay, two shapes. So I'm going to have the argument here being 0 and pi, for example, on the Eigen diagram, as we might have seen quite often from the roots of unity. So in this case, okay, what I like to do is to indicate an arbitrary coordinate p, and I call the distance from the center to p as just the x. Okay, so assume the distance from 0 to p is just arbitrarily x, okay, and it's a unit circle, so you can see the distance from C1 to p and C2 to b respectively quite easily, because it's going to be just x minus 1 from C1 and x plus 1 from C2, okay. That's great. So now let's try to multiply. Try to multiply those distance that's been separating the circle and separate dissection. In this case, then, I get the product of x minus 1 and x plus 1, which will induce the difference of a square, the x squared minus 1. The very first case that I wanted to talk about for the x to the power of n minus 1. In this case, it is when n is equal to 2. Okay, no problem. So what I like to show this is that, so now if I separate the circle n many times unison, like the roots of exactly the roots of unity, and then get the distance from those arbitrary dissection into the point P, get all the distance, and then see the product, and see if that would eventually make the expression of the x to the power of n minus 1. Okay, let's go with the n equal to 4 first. You know, we already saw the n equal to 4, meaning is x to the power of 4 minus 1, can be factorized by the linears and quadratics. And I like to see that if you can visualize using the unit circle and then the roots of unity in this case. Suppose, you know, we don't know anything about the roots of unity, so I'm going to partition these into 4 different cases, just like the roots of unity. So I got these 4 arbitrary points that's unisonly separated by the angle of a pi over 2. Okay? Hence the roots of unity. So now I got the arbitrary coordinate p, which I'm going to call the distance from the center O to p as an x. Then now you have to get those distance from the other coordinates. Well, in fact, if you look at the coordinates on the horizontal axis or the real axis, getting the distance is quite easy, because you just have to add or subtract linearly, right? Because that's the distance on the same linear axis. So if I look at the distance from C1 to P, which we already have seen before, it would be just x minus 1. Easy peasy. Lemon squeezy. Now if I go for the C3, I just have to go one further, so that's gonna be just x plus 1. No problem. Okay? Now let's try to derive the distance between C2 to P. Well, in this case, as you can tell, we can use maybe the right angle triangle and using the Pythagoras theorem, because I got the length of the height and then the base to use the Pythagoras theorem. Okay? So now if I use the Pythagoras theorem on one of those right angle triangle, right? So that was already the factorization, but suppose I knew nothing about that, and then try to use this diagram to derive that factorization, is the following. So now I got this right angle triangle here, and then I got the length here to be the square root of x squared plus 1 because of the Pythagoras theorem, because it was a 1 again, this is an x, so this is a result of the Pythagoras theorem. And make no mistake, this triangle, that triangle are congruent to each other. That means I can get the same distance here as the square root of x squared plus 1. Okay, let's try to then multiply all those lengths that we found. Up to the C3 was x plus 1. Up to C1 it was x minus 1. All right? And then the distance C4 and C2 respectively was the square root of x squared plus 1 each time. All right? So I'm going to multiply the same thing on the square root of x squared plus 1 on the purple now. So, but if you multiply this, it will become actually a quadratic. Right? But it's quite it's reasonable to deduce that, because if you think about the expression that you're going to have is using the sort of a Pythagoras, is the distance formula. It's going to have always a square root, and then within the expression it's going to be always something with the perfect square, right? Because it's Pythagoras theorem. So you already have a quadratic term lying around, but it got square rooted. But now if you every time you're doing the n dissection of the circle, you're going to have equally n many cases, even number of the same distance. So if you multiply each of them, square root will just disappear. So then you are just left with the quadratic factors. That's quite marvelous. Let's have a look at the case with the n equal to 3. The reason I did the n equal to 4 was it's easier to sketch, but you know, it's not different at all. Let's have a look. So now I'm going to have a look at the separation of a circle by three shapes So it's going to be triangular, right? And now if I have a look, so now, as you can see, all the angles are here just 2 pi over 3. You see, I divided the circle by 3 many times. So no problem. And my claim here is I want to now induce linear and quadratic vectors that will generate the x to the power of 3 minus 1, the difference of cube. So to do so, I like to see the relation of the distance from C1 to P, C2 to P, C3 to P. The product will be the same as x cubic minus 1. Let's please check the formula. Okay, so what we are going to do is the same thing. We're going to define the length from the center to the P as an x. Okay, so that's great. And then let's go from, C1 to P as just x minus 1, usual distance. But now the reason I did this as a second one, this one later than the n equal to 4, because it requires a bit of a trigonometry. So let's have a look. So now you know that I want to use the, maybe the Pythagoras theorem on this right angle triangle, right? And to do so, you need to know the height and then the base. But for that, what we can do is to use the right angle triangle, right? The trigonometry. So if you look at this right angle triangle, remember I separated this unison 3 times. So this is the equilateral triangle. So one of the angle here is pi over 3. But because it's an isosceles triangle, it's going to bisect the angle. So in fact, the angle that you have there, my friend, is a pi over 6 or 30 degree. Okay, let's keep it in radian. And then now angle to the opposite is going to be described by the sine. Remember, opposite is always something to do with the sine. Adjacent is always something to do with the cosine. So now I'm looking at 1 times a sine a pi over 6. And that one will be 1 times cosine pi over 6, for which we know it's going to be half and root 3 over 2 respectively. So now for the larger triangle that I wanted to use for the C to P, that one is going to be just root 3 over 2. This one is going to be x plus half, okay? For which then I can induce the Pythagoras theorem and get the hypotenuse, okay? Let's see the visual on that one. So again, like I said, I can get the half using the sine, okay? And the root 3 over 2 using the cosine. Easy peasy, lemon squeezy. And then on top of that, now I'm going to use the Pythagoras theorem on the larger right angle triangle like that, okay? So that we can get the length from C2 to P. All right, so then let's try to use the Pythagoras theorem on this one. So this one is it was root 3 over 2, and that one is my friend, the x plus half. So I'm using the distance, so Pythagoras theorem on this one. Let's expand and simplify. It gets like that, and then the constant term, if you add them together, will be simply just become 1. Okay, no problem. I got that. But again, this triangle, that right angle triangle are congruent, right? The right angle, shared angle, shared side, and the one equal length angle will give you the condition for the congruence. So this length will also be square root of x squared plus x plus 1. So now if you get all the product of the length that we found from point P to any other points that we separate the circle with the n equal to 3, I got the x minus 1 for the first one. The second one will be square root of x squared plus 1. The next one will be also square root of x squared plus 1 thanks to the congruence. Now if you multiply all that, you get the this will be, the x minus 1, and then the x squared plus x plus 1. If you expand by using the distribution, you actually get the x cubic minus 1. So we can actually tell that, yes, it is possible x to the power of n minus 1 to be factorized as a linear and quadratic terms always. Okay? So that's marvelous. But let's have a look at the case of x equal to 5. So n equal to 5. But for this one, it's harder to visualize, and it's actually very difficult to get those distance from the Cn to P using just a Pythagoras theorem, because it involves a lot of extensive knowledge on the trigonometry. You got to know like cosine 2 pi over 5, things like that. Right? For the n equal to 7, you have to know cosine 2 pi over 7, for example. It's very difficult to derive, although you're often asked to find sine cosine 2 pi over 5 in the exam using the complex number and binomial expansion. But when n gets larger, it's just difficult. But for this one, let's try to go back to the algebra and see if I can use the extensive knowledge of the complex number and use it for the integral. So let's have a look. So now, this reminds me of, all this discussion of separating the circle n many times is just the roots of unity, right? So I like to use the roots of unity on this one. Okay, so the simple factorization gives me that. So my job is to actually find a quadratic vector, product of quadratic vectors on this quartic polynomial using just a complex number without any visual for the n equal to 5. Let's have a look. Okay, so using the complex number, right? If I have that, I can rearrange the 1 to the other side, and then 1 is in fact the same as the argument 0 for complex numbers. It's the same as e to the power of I 0. Okay, that's how I'm going to define right now. Okay, and then if I have that form and then you want to find nth roots, we can use the roots of unity formula. Let me remind you, z to the power of n is equal to e to the power of I theta. Then z is going to be e to the power of I theta plus 2k pi over n, where k is equal to 0 to n minus 1. You know what I'm saying? So that's what I want to do. So on this one, I like to use the roots of unity. Well, the zero being argument is very simple to compute. So it's going to be just 2k pi over 5, but k is going from 0 to 4. So we have exactly 5 distinct roots. Okay, so if you have 5 distinct roots, you can find the 5 different linear factors with these complex roots on the factorization of the quantic polynomial. So let's have a look. So I got the roots here. So I just employ the linear factors given those roots, okay? But of course we don't want to describe like that because we wanted to show the quadratic factors, especially with the real coefficient, okay? And yes, one thing I want to remind you is that you have to take the advantage of the product of the linear factors that are conjugate pair. Remember, it was a very important concept when you were learning the fundamental theorem of algebra, my friend. So, for example, if you look at the 2 pi over 5 and 8 pi over 5, they're actually conjugate to each other. Why? Because if you take the conjugate here, you know, for the Euler form or cis form or polar form, your argument just becomes negative. So for that one, it would be simply just e to the power of negative 2 pi I over 5. Well, it doesn't look exactly the same as 8 pi I over 5, but you just have to rotate once. You know, if I just take one circle, which is 2 pi, if you add by 2 pi on here, it will be same as 8 pi over 5i. So it's actually the conjugate pair. And that's marvelous because if I then do the product of this linear factor and that linear factor, I'm certain that I will get a quadratic factor with just the real coefficient. Because if I quickly remind you the formula, right? If I quickly remind you the formula, my friend, the product of the linear factors given by the complex number and its conjugate pair were given as the following, right? It's just twice of the real part of the complex number and then the modulus of complex number squared. No problem. So I can do the same thing. So the real part of that will be simply just given as a cosine. So I've got this quadratic factor. And you can do the same thing for the other remaining roots with the 6 pi over so 6 pi over 5 and 8 pi over 5, I believe, or the remaining angle argument, which are conjugate to each other. You can prove it yourself. And then I can generate this quadratic factor just like that, right, very quickly. So now, instead of writing this as 5 linear factors with complex numbers being roots, I can actually describe it as linear factor as well as a quadratic factor with the real coefficient. So that's quite beautiful. And then the reason we love this is that now remember, by no chance, you know, make no mistake, you know, the whole point of doing this is so that whether we can see the integral of this. Well, you know, now I'm very happy because it's a product of a linear and quadratic. I can decompose of a over the, the linear, and then bx plus c over the quadratic, and dx plus e over quadratic, because for quadratic terms, the remainder can be up to the degree of 1, the linear term, right? So I can confidently say that I can integrate then because it would be just either logarithmic form or the inverse tangent. So if I quickly compute that for you, I've computed for you right now, but if you want to actually extend this idea for your internal assessment, if you want to explore a bit more, I strongly encourage you to actually compute yourself. This is actually a very, very good example, not only for paper 3, but also for the internal assessment. Okay, so I got this. I got the linear factor and then quadratic factors like that. That's great. But now I'm going to do the partial fraction. If you actually do the partial fraction, it comes out like that. And it looks very nasty, but in terms of the integral solution, it's not that bad because you actually have a linear, and I got a quadratic linear. Then either way, it's going to be just log or inverse tangent. So if I find the solution for you after extensive algebra, the solution will be given as such. And as you can tell, every solution is either log or the inverse tangent. It's quite marvelous, isn't it? So now, every time I have, the 1 over x to the power n minus 1 dx, I'm very confident that I can actually decompose this as a product of linear and some number of the quadratics, and hence I can actually integrate using just the logarithms and inverse time. Okay, so that really summarized the question the student had, and I think it was a beautiful, beautiful question. That's the whole point. You see, you have to ask questions during the lesson so that some people might actually answer that question only, but also extend beyond and talk about the historical significance of those problems to link with other topics, such as this was integral calculus. However, you can, as you can see, you can extend it with the complex number and especially associated with the roots of unity, right? That's why since the 17th century, the complex number has been employed in many other fields, not only just trigonometry, but also, as you can see, calculus. And study of that is known as complex analysis. So if you're interested in for your topic, a potential topic for your internal assessment or extended essay, I strongly encourage you to take it because it's a very nice topic, not only algebra, but also in terms of geometry and aesthetic visualizing. Okay? But yeah, that's pretty much it from me today. I will see you next time. Thank you very much. See you next time.